Hi, and welcome to this section of the Probability and Statistics Tutor. And in this section, we're going to cover the topic of mean and standard deviation of a binomial probability distribution that we've been studying in the last section, okay? So one thing that you need to kind of think about is in the last section, actually 2 sections ago, we presented the basic idea of what a probability distribution is, okay? And you know what it is now. It's just this function that when you put in values of your random variable, whatever it is you're trying to study, you get back the probability that value will occur. That's really what it is, okay? And then, so we talked about that. We talked about also the mean and the standard deviation in general of a probability distribution function. We had the general formulas there. And then the next section, which was the last section, we talked about the probability distribution, the binomial probability distribution, that specific probability distribution. We talked about how to calculate values and set it up and really understand how to use the tables and everything else. This section is going to tag along to the end of that, and we're going to now study the mean and the standard deviation of the binomial probability distribution, okay? So what we're learning in this section really is nothing new. It's just that we're going to work with some specific formulas that have been derived to calculate the mean and the standard deviation very, very easily of when you know it's a binomial. You can always use the general formulas that we've already talked about a couple of sections ago. You can always apply those, okay? So we're not learning anything that's replacing that information. It's just that for the binomial distribution, the formulas are actually a lot simpler. So we're going to use those, and we're going to do a couple of quick problems to show you how to do that. So first, let's go ahead and just do a little bit of review from a couple of sections ago. We know that for any probability distribution, any probability distribution you can make up, whether it's a table or a function or whatever, we know the following things, because we studied this a couple of sections ago. We know that the mean, mu, of this probability distribution function is equal to the sum along all x, all values of the random variable that you're studying, of the sum of x times the probability that x will occur. And really all this is doing, just to recap really briefly, is you're taking the values of your random variable that you're studying. This could be the number of eggs, you know, a hen lays in a day or something. And for each value, 0, 1, 2, 3, for however many you have, you're just multiplying by the probability that that thing will actually occur. And then by adding them all up, you get an average value of what the random variable is going to be. So at the end of the day, this will tell you that on average, let's say if we're talking about the number of eggs a hen may lay, this mu, this average mean value, could be 1.67. On average, the hens in this particular farm, given this data, would lay 1.67 eggs, let's say. So it's giving you the average value of this random variable because we're multiplying by their probabilities and then we're adding them all up, okay? Now, I'm going to draw an equivalent table over here for the binomial. Things actually get a little bit simpler. Okay, so that's a good thing. The mean can be simplified from this expression. For the binomial distribution, it's just equal to n, the number of trials, times the probability of success. That's it. Okay, so instead of looking at every random variable and then multiplying by f of x, which you can calculate for a binomial, you know what f of x is. We've talked about it. That's that combination of n and x, and then p to the x, and then q to the n minus x. That's that big binomial function. You could calculate all the values of f, multiply by x, and you could sum them all up and you would get the mean. Well, it's been derived that that whole process just yields this as a result. So if you know you're dealing with a binomial, you know the number of trials you're dealing with n. We just studied the binomial distribution. And if you know the probability of a success inside of each of those trials, then you just multiply the two things together and you get the mean. And we'll do some problems to illustrate that, but you can kind of think that it makes sense. I mean, if you flip a coin 10 times and you know the probability of getting a heads, which is your success, is 0.5, then you're going to be able to figure out by multiplying those two things together what the average value is, the average number of heads that you're going to get, because you're taking into account the probability of success and the total number of times that you're actually doing it. So we're going to do some problems to illustrate that. Now, in general, the variance, which is just the standard deviation squared, back a couple of sections ago, was the sum over all of x of x minus the mean squared times f of x. So we're taking the difference between the mean and the random variable that we care about, we're squaring it, and then we're multiplying by the corresponding probability. And then we add all of those things up, and we get the variance. Okay. Now I'm going to just write this down. I'm not going to really say much about it yet. The variance, which is the standard deviation squared, can be written as n times p times q. These are all things that you know for binomial distributions. Number of trials, probability of success, probability of failure inside the trial. Okay. Now the standard deviation is very simple. It's the square root of this, right? The square root of sigma squared is just going to be sigma. This is a lowercase sigma. Okay. So what you're going to get is exactly something that looks exactly the same, but with a square root around it. So you're going to have x minus mu squared times f of x. And you have all that, and you do all the summation, and you just take the square root. And then correspondingly, it's just the square root of n times p times q. So I'm actually not going to be in the business of necessarily deriving these for you here. These are things that you could go for a binomial distribution. You could go in and you could plug in what you know for the binomial distribution function and this right here, and you could simplify all this, and with some math you can figure out that it actually just equals some of the parameters, some manipulation, some of the parameters for the binomial function. So it's really convenient. You don't have to go through and tabulate all this stuff like we did a few sections ago. If you know it's binomial, this is always given to you in the problem, n and p and q. So you're always going to be able to calculate the mean here in the standard. Oops, I wrote something down wrong. Sigma is the standard deviation down here. You're going to be able to do that really quickly with just the information given to you in the problem. And this is actually, these two things here are the most important things to be able to calculate anyway, okay? So let's just expand on this a little bit, and let's recall further. Let's recall something further, okay? Let's recall three things, okay? Roughly 68% of values fall. This is for any probability distribution, not just a binomial. This is just a fact. 68% of all values fall within 1 sigma of mean. And I'm going to draw you a picture in a second, but that's why the standard deviation thing is useful. It's giving you a measure of how spread apart your values actually are. So no matter what you calculate for sigma, when you know what this value is for 1 sigma, 68% of the values are going to fit within 1 sigma plus or minus 1 sigma. Okay, the second thing we learned before was roughly 95% fall in 2 sigma. This is plus or minus 2 sigma of the mean. And then just to kind of round it out, even though you don't use this too much, 99.7%, this is roughly 99.7% fall within 3 sigma of the mean. Okay, so if you were going to draw a picture to kind of illustrate what that is, okay, so what we're going to do here is just briefly just kind of summarize what we know with regard to the standard deviation. So if this is your little probability distribution function that you're drawing here, I mean, you could easily see how you could just plot it. Okay, and let's say I was going to do that. I'm just making this up just off the cuff here, but let's say I had a probability distribution that looks something like this. Okay, now just glancing at it, you know that the average value here of the random variable that you care about is going to be roughly here somewhere between probably 3 and 4. Because you'd have to calculate it, but just by eyeballing it, that's sort of what it looks like, because you can see that there's a really strong peak that the probability of 3 is going to be very high, and so you've got some more bars over here, so it's going to shift it over a little bit. So this is roughly the mean. This is roughly the mean. It's just I'm just doing a rough back of the envelope thing here, okay? Now, if you had to calculated the standard deviation, okay, then on either side of that mean, okay, if this is the mean, right, then 1 standard deviation would be about that far. That would mean 68% of the values would fall plus or minus 1 standard deviation from the mean, okay? That's what that means, okay? And then if you calculate 2 sigma plus or minus 2 sigma, then if this is again the mean, then this might be 2 sigma, and again 2 sigma over here. So what you're really looking at is 95%, which is what we just talked about. 95% of the random variables are going to fall within 2 sigma, and if you go out to 3 sigma, 99.7, et cetera, et cetera. So what you really use the standard deviation for is a really quick way to figure out if whatever value you're looking at is likely to fall in here. Okay, what you're really trying to do is point out that because most of the data falls within 2 sigma, which is 95%. I mean, that's just sort of an arbitrary thing, but most quote-unquote 95% are going to fall within plus or minus 2 sigma, 2 standard deviations. Then what you can do is you can define what are called sort of most usual values and the maximum usual value and the minimum usual value. Let me just write it down, and it's not going to be a big deal, and we'll just talk about it here. The max, I'm going to put quotes around here, usual value is equal to the mean plus 2 sigma, and the minimum, again, usual value is equal to the mean minus 2 sigma. All this is really saying is that since most of the values are going to fall within 2 sigma, that means plus 2 sigma and minus 2 sigma on either side of the mean, 2 standard deviations, 95% of the values there. If you were doing an experiment or looking at some data of a large collection of people and you calculated the mean and the standard deviation, you would know that with pretty good certainty that most of these values, 95% of them, are going to fall within plus or minus 2 standard deviations of the mean. That's all that means here, okay? So if you were looking at a data point and trying to figure out if it was an outlier or not, is this data point, likely is this an unlikely occurrence or a likely occurrence? Well, you would use the standard deviation to sort of figure that out, and we're going to do that with the problems. It's sort of an arbitrary thing, but because most of the values, quote-unquote 95%, fall within plus or minus 2 sigma, anything that falls outside of that is sort of going to be considered the outliers. They're going to be considered like the data points they're in your data set, but they're not really indicative of the main body of data you have. It would be kind of like on an exam, in a classroom, you have a mean of, let's say the average value is 80. That's what the average value was on the test. And the standard deviation, let's say, was 5 points, okay? So 1 sigma is 5 points, 2 sigma would be 10 points. So that would mean that, in practical example, for the class with an average of 80, most values, 95% of the class is going to get within plus or minus 2 sigma, plus or minus 10 points of the mean. So that means most of the class would fall between 70 and 90. That's 10 points on either side of the mean because we calculated the standard deviation, okay? So then if a student comes in and says, yeah, I bombed that thing, I got a 35 on the test. Well, you would look at him and you'd say, well, I'm really sorry you got a 35 on the test, but you're a statistical outlier, okay? Because the rest of us had a mean of 80 and a standard deviation of 5, so 2 sigma was 2 standard deviations was 10. 95% of the class is going to get between plus and minus 10 points of the mean, between 70 and 90, and I'm sorry that you got a 35, but you are a statistical outlier. So that's sort of why that's useful. You can look at data, and you can look at points, and you can figure out if they're still part of the set, they're still part of your data, and they still participate in calculating everything. It's just that it's really useful to know if this person or that person is representing sort of the main body of the class, or are they just sort of a curve buster, so to speak. It also could work the other way. You could have a mean of 60 points, 60, grade of 60, standard deviation, again 5, so 2 sigma is 10. And so you could say that, well, the mean is 60. Most of the students, plus 95% of them, are going to go between maybe 50 and 70. If the mean is 60, well, then you have the genius over here that scores a 95 on the test. And you're not very happy that he did that, but you also kind of know that, well, hey, he's a statistical outlier. 95% of us fell within 2 standard deviations of the mean, so there's only 1 or maybe 2 people that got anything outside of that. That's really what the concept of standard deviation is for. So let's go ahead and work a couple of quick problems and get some experience with calculating the mean and the standard deviation of a binomial distribution, and looking at this outlier business and see if we can calculate that. Okay, the first problem says there are 10 true-false questions on a test. A student guesses at all of the questions. Okay, what is the mean and the standard deviation of this situation here? Okay, so first thing we're going to look at is we're going to see, is this a binomial distribution or not? Okay, 10 true or false questions. So there's 10 trials. We know the probability of success or failure because it's true-false. It's going to be 50% true and 50% false. Okay, so we know that. We know that they're guessing, It seems to follow every rule of a binomial distribution. They're independent trials, no event influences any other event, everything stays constant, there's only two possible choices for every little trial, and there's a fixed number of trials, so it is binomial, okay? And also what you can do is you can sort of look at these things and write down what you know right away. You know the probability of success on each question is 0.5 because it's a true-false test. So either you're going to guess right or you're going to guess wrong. So the probability of getting a question right is 0.5. You know that the number of trials is equal to 10 because there's 10 questions. So even without writing down f of x and calculating the binomial distribution, you have enough information to actually calculate the mean, which is n times p, okay? Which is 10 times 0.5, which is 5, okay? So the mean is equal to 5. So if I were looking at this from the point of view of how many questions correct, and that's what I'm really looking at, the random variable is the number of questions correct, then what this is going to tell me is that if I guess at a 10-question true-false test, the mean number of questions I'm going to get right is going to be 5. And that makes total sense with your everyday experience. You guess on 10 questions and they're true and false, then you're going to probably get 5 of them right on average. Some days you might get 3 right, some days you might get 6 right. If you did this a whole bunch of times, on average you would see that you would get only 5 of them right, okay? So we also want to go ahead and calculate the standard deviation to this, which we can do with exactly the same information, okay? Calculate the mean. The standard deviation is equal to, if you remember, the square root of n times p times q, which is the square root of n is 10 times p is 0.5 times q is 0.5. By the way, what is q? Probability of success is 0.5. Then the probability of failure is 0.5 also, 1 minus p. Also, you can think of it in terms of getting a question wrong is the same probability on a true-false test. So n times p times q. So the standard deviation here is going to be the square root of 2.5. So the standard deviation is going to be 1.58. And what this means is that if you guess on this test, the average number of correct answers is going to be 5, but the standard deviation is going to be 1.58. That means that, again, 68% of, if you did this a whole bunch of times, 68% of the people are going to fall within getting plus or minus 1.58 questions right. So almost 1.5 questions, almost 2 questions you could think right. So the average is going to be 5, but if you did this experiment a whole bunch of times and asked a whole bunch of people to guess, some of them are going to get 5 right, some of them are going to get 4 right, some of them are going to get 6 right. But if you did it a whole bunch of times and looked at what everyone did, then it would show that 68% of the people would roughly get between, let's say if it's number 5 there for the average of 5, plus or minus 1.58 questions right, okay? And 2 sigma is 2 times this, roughly 3. Then 95% of the people would be within plus or minus 3 points of the mean. So the follow-up question to illustrate that is, would it be unusual for a student to get 7 answers correct? That's what we want to know next. Would it be unusual? So again, we know that some people can guess and get 5 right, and some people can get 6 right, and some people can guess and get 3 right. We also know that some people can guess and just be really lucky and get 10 of them right, but they're going to be very unlikely to happen. Okay, so our question is, if they get 7 answers right, is that unusual? And we're going to use the concept of the standard deviation to tell us that, because we know that 95% of the people fall within plus or minus 2 sigma, so the max unusual questions that you would get correct would be the mean plus 2 sigma, which would be the mean of 5 plus 2 times 1.58. Okay, so the maximum unusual number of questions that you would get right is 8.16. There's nothing magical about 8.16. It just means that on average, 95% of the people are not going to get that many questions right. They're going to get either 8.16 or less, the mean on either side of the mean by 2 sigma. Okay, right. So before we actually answer the question, let's go ahead and calculate the minimum unusual. That's going to be the mean minus 2 sigma, because again I said it's plus or minus 2 sigma. So it's 5 minus 2 times 1.58. And when you do this math here, 2 times 1.58, 5 minus that, then what you're going to get is 1.84 questions right. What do all these numbers mean? Okay. The average number of correct answers on this test is going to be 5. What this is saying is we calculate the maximum unusual and minimum unusual. Okay? If the average number of correct answers is 5, okay, then what this is saying is the maximum number of unusual is 8.16, the minimum unusual is 1.84. So that means 95% of the people are going to get between 1.84 and 8.16 questions correct. If anybody gets less than 1.84, he's going to be statistically an outlier because he's not in the majority of the people. Like we said, 95% of the people are going to get between this many and this many questions right. And also, if you get someone that scores higher than 8.16, maybe getting 9 questions or 10 questions correct on the test, they're going to be considered an outlier. They're going to be considered unusual for the same reason, because 95% of the people should score between this and this, okay, for this binomial distribution. So the question actually said, if someone scored 7 correct answers, would that be unusual? Well, if somebody scores 7 correct answers, that's going to be somewhere right around there, and that's going to fall well within 2 sigma, 2 standard deviations of the mean, and so that's how you define if something's unusual or not. So no, it's not unusual for someone to get 7 questions correct. It would be unusual if someone got 9 or 10 questions correct because of exactly what we're talking about here. Now the next question says, when playing roulette, the probability of winning on a single spin is 1 in 38, okay? If you bet on a single number for 100 spins in a row, what is the mean and standard deviation of the number of times that you'll win? Okay, so you're playing roulette, which means you're doing 100 trial, 100 spins of the wheel. Okay, the probability of success is 1 in 38, so it's a binomial distribution, fixed probability, independent events, fixed number of spins in. Okay, we want to know what the mean and the standard deviation is. Okay, so we know that n is equal to 100 because we're spinning the wheel 100 times. We know the probability of getting the answer that we want to win is 1 in 38. Okay? And we also know that q, which is the probability of losing on every spin, is 1 minus p, which is 1 minus 1 over 38, which is very easy to do because I can rewrite this as 38 over 38 minus 1 over 38. 38 over 38 is 1. So then q is going to be equal to 37 over 38. This is the probability of losing on a single spin. It's pretty high because, I mean, the likelihood is you're going to actually lose on that single spin, okay? So the next thing we want to do is calculate the mean. Because it's binomial, and only because it's binomial, we can use the shortened formula here, n times p. The mean is equal to n times p. So it's going to be 100 times 1 over 38. 100 times 1 over 38, and when you actually do this and get the decimal, what you'll get is 2.63. So the mean is, if I spin the wheel 100 times in roulette with these probabilities of winning, the average number of times I'm going to win is only going to be 2.63 times. Not very many times out of 100 spins, okay? The standard deviation is the square root of npq, which is the square root of n is 100, and p is 1 over 38, and q is 37 over 38. Okay, that's again specifically for the binomial. And then when you actually multiply all this together and take the square root and get your decimal out of it, what you're going to get is 1.6. So again, the mean is that I'm going to win this roulette 2.63 times out of 100, and the standard deviation means that plus or minus 1.6 around the mean, okay? So that really means that if I run this experiment a whole bunch of times with a whole bunch of people, 68% of the people are going to always get plus or minus 1.6 around the mean. That's how many times they'll win. And 95% of everybody, if I run this experiment a whole bunch of times, is going to, 95% is only going to win roulette plus or minus 2 sigma around the mean. That's what that means, okay? So the follow-up question is, would it be unusual not to win once in 100 spins? Would it be unusual not to win once in 100 spins? So you have this roulette wheel. It's got a certain probability of winning. You spin it 100 times, and let's say you just have a really unlucky day and you don't actually win at all. Even though the probability of winning is 1 in 38, you spin the wheel 100 times and you don't win at all. Question is, statistically speaking, from the terms of the standard deviation and everything we're talking about, would that be unusual or not? So when you see the word unusual, start thinking in terms of your standard deviation, okay? And so we're going to say here that the maximum unusual number of wins is going to be equal to the mean number of wins plus 2 standard deviations. That's 95% of the people are going to be plus or minus 2 sigma. So the mean was 2.63 plus 2 times sigma was 1.6, and when you do this math, 2.63 plus 2 times 1.6, what you're going to get out of it is 5.38 wins. So before we answer the question, let's go ahead and calculate the minimum unusual wins. Is the mean minus 2 sigma. Okay? The mean was 2.63 minus 2 sigma, which is 1.6. Now, the interesting thing is, if you actually take 2.63 minus 2 times 1.6, you're actually going to get negative 0.5. You're going to get a negative number. Okay, so what this means is, it doesn't mean you're going to win negative number of times. All it means is that if you run this experiment a whole bunch of times, the average number of people is going to win 2.63 times. But statistically speaking, 95% of everybody that spins the wheel, because some people might win 2 times, some people might win 3 times, some people might win 1 time, some people might get really lucky and win 7 times. So what we're trying to do is we're trying to define some cutoffs. Beyond what number of wins is it considered unusual or not? So we define the maximum and the minimum, okay? And the question is it unusual if we actually don't win at all? Well, look at what's happened here. What we're saying here is the average number of people is going to win 2.63 times, but 95% of us are going to win between negative 0.5 and 5.38 times, okay? Now, there's no such thing as a negative win. What this is really saying is that 0, the probability of winning 0 times, or actually spinning the wheel and winning 0, is well within 2 standard deviations of the mean, okay? So what that means is it's quite possible for someone to go into the roulette house, statistically speaking, without being an outlier, and spin the wheel and win 0. Because normally you should get positive numbers for everything. We actually got a negative number for the minimum number of wins. All that means is that statistically speaking, 0 falls within 2 standard deviations of the mean. So getting 0 wins is not really unusual. So I'll just write it down like that. Getting 0 wins is not unusual. And again, it's all defined in terms of what we talked about before. It just means 95% of us are going to be between those boundaries. So getting 0 is not really out of bounds. It wouldn't be considered an incredible streak of luck. However, if you went in there and you spun that wheel and you won 57 times in a row and you cleaned the house out and tried to pack your bags with $50 million because you won in roulette, and you won because you spun the wheel and you had 57 wins in a row, these guys know all about statistics. It's saying the average number of spins is going to be 2.6 that you'll win out of 100, and the maximum, statistically speaking, 95% of us are always going to get less than 5.3 wins. If you try to spin the wheel and win 57 times, they're going to assume you have rigged the game somehow and that you are doing something, either, I don't even know how you would do it, but you're somehow cheating. So they're obviously going to be onto that. So that's what's really useful about standard deviation, is figuring out what is unusual and what is not. It's all about figuring out, like I said, how squished up your data set is or how spread apart it is. The standard deviation really measures that, and it tells you if certain data points, if they're outliers or not, if they're falling in that main body of the data that you have, okay? So this section was a short one on mean and standard deviation of binomial distributions. If you see that it's a binomial, you can certainly calculate f of x. You can certainly use the original formulas that we had defined for probability distributions in general, but it's much faster and easier to go ahead and just use these if you know it's a binomial, because it'll lead to the right answer with less math, and that's always a good thing.